Algebra 2 students, in our faculty meeting today, I realized we have a lot of stuff to cover and not a whole lot of time. So from your classwork today, I think you could figure out this formula. This is a formula for simple exponential growth or decay. A is the amount you have present after a certain time t. So t is time, and as time passes, A is the amount present. P is often called the principal. In an economic sense, the principal is the starting amount, the initial amount, what you have to begin with. Your initial investment is sometimes called the principal. 1 stands for 100%. R stands for rate. You have to be careful because this needs to be entered as a decimal into the formula, but it's often given as a percent. I will hire no Algebra 2 students as bankers because they'll put a 3 here when it's 3%, which is effectively giving me a 300% interest rate. And I'm glad that you're at the bank. If I'm the borrower or the client, I am not happy if you're charging me interest. And then T stands for time. This is called simple interest because it only allows a very simple calculation per unit of time. So this would be after 1 year adding a certain percentage or decreasing a certain amount. So if you know things are decreasing by 10%, you could put a minus 0.1 here. Then you can get your decay model, right? So if R is equal to 3%, you would have this. A equals P times 1.03 to the T. You could see that would be exponential growth because the base is bigger than 1. If R was decay with 3%, it would be 0.97 to the T. And then, yes, that would look something like this because it's decay. Now, these graphs are not to scale. There's no axes. This would be T, this would be A, this would be T, this would be A. But because, decay and growth are based on the value of the base, I just wanted to show you that. So we have a special formula that we use sometimes called the compound interest formula, and it looks like this. And everything is the same except now N stands for number of times compounded. So you can compound interest daily or monthly or yearly. If it's a year, you would put a 1 here and a 1 here, provided the rate is given in some unit of time, right? So we might talk about 3% per year. If we have 3% per year, then that means we would want to have N, if it was 1 year or yearly interest, that would be a 1. Then we could do monthly, and this would be a 12, and this would be a 12. And the idea here is you're not going to get 3% interest the whole year or every single time. You're going to get it compounded over a year. So if I said 3% interest per month or compounded monthly, sorry, not 3% per month, that'd be great. 3% compounded monthly would look like this. 0.03 divided by 12. That is equal to what? 3 goes into that 4 times. So that would be 0.0025. So every month I'm going to give you 0.25% interest. Over 12 months, that's going to total 3%, but I'm going to give you 1/4 each time. And instead of giving, then when we calculate, I have to actually calculate the number of years times 12 because I'm not doing interest once a year anymore. I'm doing it 12 times a year. Good, so let's do a practice problem, and you can see the difference here. Let's say we had $1,000 investment, and you want your calculator here. We have a rate of 4.25%. Let's calculate the interest after 5 years. So this is 4.25% per year. Let's calculate 3 different examples. Let's do 1 when N equals 1, so that would be compounded yearly. Let's do n equals 4. That's what we call quarterly. Let's do n equals 12. That would be monthly. And let's do n equals 365. That would be daily. Pause the video, plug these numbers into your calculator, and see what the amount of money you would have in your account if you put in $1,000 at 4.25% interest per year for 5 years, compounded at these 4 different levels. Start with the formula. A equals P times 1 plus R over N to the T. NT. For n equals 1, you will get the simple interest formula. So that's 1,000 times 1 plus 0.0425 to the 1 times 5. When you calculate that, I'm doing it on my calculator as we speak, 1,000 times 1 plus 0.0425, close that, raised to the 5, you should get 31 and 35 cents. Always round these problems to the hundredth place when we're talking about money. All right, so that's simple interest. After 5 years, you only have $231.35 earned in interest. Now, that's not bad for doing a whole bunch of nothing, right? Just putting your money away and not touching it. If we did quarterly interest, if you are careful with your calculator, you can enter it exactly as it looks here. You divide this here, 0.0425, all divided by 4, and then raised to the 4 times 5. If you use parentheses in the power, you should be able to do this all in one step, which is what I'm doing right now. I'm entering things in, and I get $1,235.38. So look, it was better, almost a little over $4 better to go quarterly. If we did 12 monthly. So now the cool thing about my calculator is I can just go in and change that 4 from the last calculation to a 12. I used parentheses. I can change that second 4 to a 12. And now I get, with monthly interest, or interest compounded monthly, I get $1,236.30. All right, even more money, almost $1 more than that. We're $5 better than this, just about. And then lastly, if I change it to 365, interest compounded daily, I end up getting even more money, and that amount is only slightly better than monthly. And this is when you take interest every day, you get $1,236.75. Good. Now, how does this work? Generally, how this works. If you are lending the money to the bank will give you simple interest. Maybe I'm actually getting monthly interest with my credit union. It's not great, but it's something. And they compound it every month based on the balance at the end of the month. I know that student loans are compounded daily. So the money you have to pay back is being charged interest every day. The money the bank is borrowing from you, they're only going to give you interest once a month versus once a day. So why do they do that? Well, they do it because they can. And that's how capitalism works. Yay. All right. Looking at this formula, a famous mathematician isolated part of it and said, okay, I'm going to look at this. I'm going to assume a rate of 100%. I'm going to assume a time of 1 year, and I'm just going to increase the n. And what that mathematician found is that as n got bigger and bigger, 1 plus 1 over n to the nth power approached a value. And that value was something around 2.71828, blah, 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 goes on forever, no distinct pattern. He realized this was an irrational number, and being the vain mathematician that he was, he gave it a name like we gave pi a name, except this one he named after himself. His name was Euler, so that's pronounced Euler. It's German, and he named it E after himself. Good? So we use this number. What was interesting is it's talking about n being infinity. So this idea in compound interest lends itself to interest compounded continuously. The way you want to think about continuous interest is it's interest every instant that the money is being borrowed. Another way to think about continuous growth or continuous decay is it's the way that things in this world replicate or decay. Radioactive material doesn't wait around for the end of the day to decrease by a certain amount. It's always decreasing. It's a continuous rate of decrease. So what Euler did was he came up with this formula and said, we can talk about continuous interest. Continuous. Right, that's not however you spell it. Continuous interest. Sorry about the poor spelling. And it's the same idea. A is the amount present after time. P is the principal. E is just a number. It's like pi. It's on your calculator. E to a power is right above the ln button. So it's right next to the number 4, and it says e to the x. You can also just get the e number by using, on the fancy calculator, right above the division symbol. So this is just a number. It's your base. And then the rate can be any percentage entered as a decimal, either positive or negative, and t is time. So let's go back to that example that we did earlier. If you took $1,000 at 4.25% compounded continuously for 5 years, it would look like this. Again, you reach for your calculator and you do 1,000. Then you use that second ln button. ln stands for natural log. We'll get to that later this unit. Use a parenthesis, and you get, with continuous interest, you get 1,236.77. So it does slightly more than the other examples. This is what you want to be using for most bacteria, the way medicine comes out of your body, things like that. Now that we've got this new number, I also want to talk to you about y equals e to the x. Here's the graph y equals e to the x. It looks something like this. It has the point 0, 1. It has the point 1, e. And it has the point -1, 1 over e. Another good function to know with in relation to that would be this one here. That's the graph 3 to the x, right? Because if e is about 2.718 blah, 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 I know that 3 to the x is slightly above it. So here's the point 1, 3. Here's the point 0, 1. And here's the point -1, 1 over 3, and I'm sure you guys noticed this mistake. This is terrible. -1, 1 over e. Sorry about that. And then another important function to know would be this one. Again, graphs not drawn to scale. This would be the graph 2 to the x. Here's the point 1, 2. Notice that that point is below e, but this point right here, that's the point -1, 1 over 2. So tomorrow in class, we're going to do a lot with E. That's going to include graphing things that look like this, and then graphing things that look like this. So we'll get to practice transformations again, and then we'll do some more word problems with compounded interest and continuous interest. All right, have a good day. Not my best video. I felt like I was stumbling all over my words. I'm sorry, but the information's there. Peace.